This question is about the elements in group 2. Describe the structure and bonding in magnesium. So magnesium is a metal, so its structure is giant metallic lattice Okay, and so when you're a giant metallic lattice, you have, with strong attractions, in fact I'm going to write forces of attraction. So when we ask to describe bonding, we want to say what forces there are and what they're between. So they're between the Mg2 plus ions and delocalized, because this is metallic, delocalized electrons. State the trend in atomic radius going down group 2. So as you go down group 2 from magnesium to barium, if you think about what's happening as you go down group 2, magnesium's got 2 shells and calcium's got 3 shells and strontium's got 4 shells and so on. We're increasing the number of shells, and so the size will increase. So we want to say that there are more shells or energy levels and that is why our size increases. Give an equation including state symbols for the reaction of magnesium with steam. So magnesium is a solid and steam is H2O gas. We have to remember that when we use steam, that what we see is a sort of bright white light and then some white solid forming, and that white solid is magnesium oxide, and we're getting hydrogen gas being given off. We just need to check our balancing. Well, it's balanced. So what would we see? We'd see a bright white light as the magnesium oxide forms. And we'd see white solid forming. Like a ash off a fire. What you must not say is precipitate, because there are no solutions here, so you can't form a precipitate from a solid and a gas. It's just a solid forms. The sulfates of the element in group 2 have different solubilities. State the formula of the least soluble of these sulfates. Well, barium sulfate is the insoluble sulfate. And it says give a use for this sulfate, and the use of barium sulfate is in as a contrast agent in X-rays. So it makes internal organs that don't have any X-ray absorbing things show up because the barium sulfate absorbs the X-rays. Sample of strontium is made of 3 isotopes. It contains 83% by mass strontium 88 and has an AR of 87.3. Calculate the percentage of the other 2. So what I'm going to do is I'm just going to write out what we've got. We've got an 86, an 87 and an 88. We know that we've got 83%. Okay, so this is our mass number and our percentage. So what we know is if we had X% of 86, we know the total of the abundances needs to be 100. So this one here, the 87 one, must be 100 minus the 83 that we've already got, which gives us 17, minus the X that we've already got. Now if we add up these 3 percentages, it will total 100. So X, 17 minus X and 83 adds up to 100. We then know that when we're calculating AR, it's the sum of the mass number times the abundance of all the isotopes. It's the weighted average mass of all the isotopes. We're going to divide it by the total abundance. So it told us that the AR was 87.73 is equal to 86 times x plus 87 times 17 minus x plus 88 times 83, all divided by 100. So I'm going to do two things at once. I'm going to multiply both sides by 100 and then start expanding my brackets. So 87 times 17, 1479. And then I'm going to do minus 87x, because I'm timesing 87 by minus x, and then I've got 88 times 83, 17304. And take all the numbers over to the right hand side. So I've got 86x and minus 87x is minus x. I'm doing 8773 minus 1479 minus 7304. That's coming out to minus 10. So x equals 10. So if x is 10, then 17 minus 10 is 7. So our 10% was our 86, and our 87 was 7%. Magnesium hydroxide is used as an antacid to treat indigestion. A student does an experiment to determine the percentage by mass of magnesium hydroxide in an indigestion tablet. 40 centimetres cubed of 0.2 mole per decimetre cubed HCl, which is in excess, is added to the 0.2 grams of the tablet and swirled thoroughly. All the magnesium hydroxide reacts. The amount of HCl remaining after this titration is determined with titration with sodium hydroxide, and it's told us the moles of sodium hydroxide. So we've got a big bunch of hydrochloric acid, an excess. Some of it reacts with the magnesium hydroxide. So this is all hydrochloric acid. Some of it reacts with the magnesium hydroxide. The rest reacts with the sodium hydroxide. Now, they haven't given you an equation for the sodium hydroxide. That's because it's a straightforward 1-to-1. We've got to calculate the percentage by mass of magnesium hydroxide in the indigestion tablet. Well, what we can see here is, even if we're a bit overwhelmed by all the data, is there's definitely two things we can calculate moles of. So the first thing I would calculate moles of is how much sodium hydroxide was needed. So it was 29.25 centimetres cubed. So I'm going to turn that into decimetres cubed, times by 0.1 mole per decimetre cubed. So 2.925 times 10 to the minus 3 moles of NaOH, which, if we look at the equation, means the number of moles of HCl reacted with the NaOH is the same, 2.925 times 10 to the minus 3. So this section here is 2.925 times 10 to the minus 3. How much HCl did I put in total? So the number of moles of HCl at the start, it was 40 centimetres cubed, so again into decimetres, times 0.2, and we're getting 8 times 10 to the minus 3. So the whole of this is 8 times 10 to the minus 3 moles. So how much HCl reacted with the MgOH2? So the number of moles of HCl reacting with Mg brackets OH twice. So if the total is 8 times 10 to the minus 3 and 2.925 times 10 to the minus 3 were left to react with HCl, then the difference must have reacted with the magnesium hydroxide. That's 5.075 times 10 to the minus 3 moles reacting with the magnesium hydroxide. So then if we go back up to our equation with the magnesium hydroxide, we can see that the ratio is 1 to 2. So if we want to know the number of moles of magnesium hydroxide, if the ratio is 1 MgOH twice to HCl to 2 HCl's, then we need to take our answer that we've just calculated and divide by 2. We get 2.5375 times 10 to the minus 3 moles. So now if we've got moles, we can find mass. Mass is Mr. Moles. So we use our periodic table to add up magnesium hydroxide, so 24.3 and 2 lots of 16 add 1, which is 17. If you add that up, you get 58.3. You're going to multiply that by the number of moles to get the mass in grams. That's 0.1479 grams. And the question is calculate it as a percentage of the tablet. The tablet weighed 0.2 grams. So as a percentage, it's 0.1479 divided by 0.2 times 100. And that is coming to 73.968. Or if we round that up to 3 significant figures, it hasn't told us a number of significant figures, so you could copy your calculator screen, but to 3 significant figures, that's 74.0%.